Collisions in two dimensions is going to be the topic of this lesson in my brand new physics playlist, which once again will cover a full year of university algebra-based physics. Now in the last lesson we talked about collisions in one dimension. Now we're moving on, progressing to talking about them in two dimensions. My name is Chad and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So now we're going to deal with momentum in two dimensions. And the big thing you're going to see different here is that instead of just saying momentum is conserved both for elastic and inelastic collisions with one equation, we've now got to say it with two equations, both in the x direction and the y direction. So momentum is a vector, and so we're going to have to break it up into components. And again, momentum is going to be conserved for both elastic and inelastic collisions. Now, kinetic energy is still only conserved for elastic collisions. But again, kinetic energy and energy in general is a scalar, not a vector, and there's no components for it to be broken up into. And it's still just going to be a single equation representing the conservation of kinetic energy for elastic collisions. So we see then for elastic collisions, we may have as many as 3 relevant equations, and for inelastic and perfectly inelastic, so 2 relevant equations for that conservation of momentum. Let's jump into working some problems and see how this plays out. Now I know what you're thinking. You're saying, Chad, I watched the last lesson. You told us we were done with blue and red balls. That was for the last lesson that we were done with blue and red balls. But unfortunately, we're dealing with blue and red balls, at least in this question, once again. Sorry. All right, question says, a 100.0 gram blue ball is moving north with a velocity of 10.0 meters per second, while a 100.0 gram red ball is moving west with a velocity of 2.0 meters per second before a perfectly inelastic collision occurs. Think about what that implies, and we're going to tell you right in the question. So after they collide, the balls stick together. So if you didn't recall that perfectly inelastic collision, the hallmark of that is that the two objects stick together after the collision. The question tells it to you. So but the final part of the question here is, what is their final velocity? So we're dealing with a perfectly inelastic collision, and so now momentum is conserved, but we got to say that momentum in the x direction is conserved and momentum in the y direction is conserved, and see how this plays out. So we'll start with that x direction. And so here we'll say that m1 v1 in the x direction initial plus m2 v2 in the x direction initial equals m1 v1 in the x direction final plus m2 v2 in the x direction final. Now you might recall that these two objects are moving together. And so as such, at least they are after the collision, and so as such, v1x final and v2x final are the same velocity. The two objects are stuck together and are moving together, and so the x component of their velocity is the same in both cases. So, and because of that, we can simplify the right-hand side just a little bit and factor out that common v1 or v final velocity. And so in this case, we'll have m1 plus m2 times just plain old v final, and we should say the x component of the velocity v final. All right, and so it looks very similar to what we saw for perfectly inelastic collisions before, where the two objects are stuck together and we can factor out the common velocity they have and put their masses together. All right, same thing is going to hold true of the momentum in the y direction. So m1 v1 in the y direction initial plus m2 v2 in the y direction initial equals m1 plus m2 times the y direction final. And again, we don't have to label it 1 or 2 because it's just the common velocity of both of them. And now we can start plugging numbers in. And keep in mind that 100.0 grams is 0.1 kilograms. So I'm going to put things in SI units, but I'm going to leave all the units off so we don't get lost in the units in algebra. But as long as we put everything in SI units, everything's going to work out just fine. And so in this case, we've got 0.1 kilograms times an initial velocity here of 0 in the x direction. So what's nice is this is perfectly in the y direction, so whereas the red ball's perfectly in the x direction, and I don't have to actually break these into components with any kind of sines and cosines because it's either all y or all x, which is going to make this a little bit easier. All right, so v1x is 0. This term effectively goes to 0. So, but m2, again, also 0.1 kilograms times 2, and in this case, I'm going to make that negative. So I'll make west negative and east positive by, common convention here. So that's going to be negative 2 meters per second. And that's going to equal, in this case, 0.1 plus 0.1 would be 0.2 kilograms times their common velocity component in the x direction. All right, so we'll do the same thing for the y component now. And so for the y component, we can see that it's all the blue ball, none of the red ball. It's this term that actually is going to end up being 0. And so in this case, we're going to have 0.1 times, and up is the positive y direction, so times positive 10 meters per second. So plus 0 is going to equal total mass of 0.1 plus 0.1 or 0.2 kilograms times that Vy final. All right, so from here, we've now got two equations. We've also got two unknowns. We've got the x direction's velocity, the x component of the velocity in that equation. We've got the y component in this direction. So but rather than solving a system of equations, so in this case, a little bit easier than that because we only have one variable in either of the equations, so you can just solve for it directly. So if we take a look here, and again, this was 0, so 0.1 times negative 2 is negative 0.2, and then when we divide by 0.2, we're going to find out that the final x component velocity is going to equal negative 1 meter per second. If we put that in proper sig figs, we're going to need 2 sig figs here, so negative 1.0 meters per second. That's the x component. Same thing for the y component here, so 0.1 times 10 is 1. And then divided by 0.2 is going to be 5. And so your final y component is going to equal 5.0 meters per second, expressed in 2 sig figs. And now we've got to take those components and put them back together to get both the overall magnitude as well as the direction. So you might recall we're going to use the Pythagorean theorem. So Vx squared plus Vy squared is going to equal V overall squared, which I'll call VR squared. And so in this case, we've got negative 1 squared plus 5 squared equals VR squared. And we can see that our overall velocity vector here is going to equal 1 squared is 1, 5 squared is 25, 25 plus 1 is 26. And the square root of 26 should be just over 5. In this case, 5.1 if we round to 2 sig figs. So it's 5.099. Round that up to 5.1 meters per second. And now we need a direction. So we can kind of see that if we added these in a tip to tail fashion, so if we put one of these up and then one of these off this way, the overall vector would point up and to the left, so to speak. And the question is, what's the angle? Well, again, we're going to get that angle with respect to the x-axis, and we do that with the tangent of the tangent function. So tangent theta equals Vy over Vx, where theta is the angle with respect to that x-axis. And so theta is going to equal the inverse tangent of Vy over Vx, and Vy was 5 meters per second. And I'll leave the units off yet again. So, and Vx was 1 meter per second. So the inverse tangent of 5 effectively. And that's going to be 78.69 degrees. And once again, I think we're going to end up rounding this to 2 sig figs. Yeah. And so we're just going to round that up. 78.69 is going to round up to 79 degrees. Okay, well, let's get better at that. So 79 degrees. Because here we're saying above the negative x-axis is what we're saying, 79 degrees. Well, what does that really mean? Well, in this case, that's going to be anchored to the west. And we're going to be going north of that west axis, if you will. So it's 79 degrees north of west. And so the overall velocity after this perfectly inelastic collision is 5.1 meters per second at an angle of 79 degrees north of west. All right, as you're about to see, the second problem here is going to be just a little bit more challenging than the first one. So it says a cue ball traveling at 5.0 meters per second makes a glancing elastic collision with a second ball of equal mass that is initially at rest. The cue ball deflects from its original direction 53.1 degrees after the collision with a speed of 3.0 meters per second. What is the speed and direction of the other ball after the collision? Okay, so here's our before picture. We can see that, yep, we got a cue ball here moving with a velocity of 5.0 meters per second towards a second ball that is stationary, initially at rest. So and we're going to do a glancing collision. A glancing collision means that instead of being dead on, we're actually going to hit it off to the side on one side or the other. If you hit it off on the top side, it's going to deflect downward, the cue ball kind of off upward, so or vice versa if you have it glancing off the bottom side. So in this case, though, notice directions aren't really defined in the problem. It just says that, the cue ball's hit and it's going to head towards the second ball into a glancing collision. Well, I happen to draw it this way that, the velocity is in the positive x direction or is east or something like that, but it's arbitrary in this case. You could have made it north, you could have made it south, you could have made it west, you could have made it in the negative x or negative y or positive y direction. It's arbitrary. But once you choose a direction and you have the liberty to do so, everything else in the problem is going to be relative to the direction you've chosen. And so in this case, that's our before picture. Let's take a look at our after picture. And so the cue ball here is going to deflect 53.1 degrees away from the original direction. Well, the way I've drawn that could be 53.1 degrees above the positive x-axis or below the positive x-axis. And it's arbitrary. It's my choice. We've got liberty to draw it how we want to in this case because it's not defined in the problem. Well, I'm going to have that go upward. And so that's 53.1 degrees. So, and then what's true about our second ball here? Well, in this case, if the cue ball is deflecting upward, that means I must have hit it up on the top side here to cause the second ball to deflect off and downward to some extent. How far? I don't know. And since we don't know, we're going to call that angle theta in this case. Okay, so that's kind of the setup for the problem. We've got our before condition, we've got our after condition, before and after the collision. So now let's talk about our equation. So we're told this is an elastic glancing collision. Because it's elastic, we have potential of having up to 3 equations. Conservation of momentum, both in the x direction and the y direction, and then conservation of kinetic energy. So that's typically where we're going to start, and I definitely recommend starting always with conservation of momentum on any collision problem. All right, so if we start with the x component, so conservation of momentum in the x direction. So in this case, if we kind of write it out generically, we're going to have m1 v1x initial plus m2 v2x final equals m1 v1x. Oh, let's get that. That's actually initial as well. Now it's final screwed up my labels here. m2 v2x final. Okay, so that's generic here. So except we've kind of added more variables than we need. We're told that we have a cue ball and then a second ball of equal mass. Well, I wrote m1 and m2 because that's standard convention. If they were different masses, we'd need to label them differently. But in this case, they're the same, and so you can make them the same label. You can make them both m1, or even just simply m would probably be even more customary. And so here I'm going to eliminate the labels on the masses since it's the same mass, and we have just one variable for mass, not two. And that's going to make this a little bit easier. The other thing we can see is that every term has mass in it. The mass was not given because it doesn't have to be. That mass term is just going to fall right out. We can divide it right out. Cancels right out of the expression. That's going to make this a little bit easier as well. Now the other part here though, we were told it was 3.0 meters per second afterward and stuff like that. So that's going to become important when we start trying to find its x component over here. Well, initially the x component, the way I've drawn it, it's all in the x direction. And so that initial velocity of the first ball is going to be 5 meters per second. I'll just make it 5. But notice the second ball was stationary. Its initial momentum was 0 in any dimension. It was stationary. Then on the other side, here's where we're going to have a little fun. So in this case, we're going to have to find the components. We're not going to use the overall vector, resultant vector of 3 meters per second. We need just the x component. And in this case, we can break this up into x and y components. The x component is going to be 3 times the cosine of 53.1 degrees. And the y component is going to be 3 meters per second. Let's draw that a little more cleanly. 3 meters per second times the sine of 53.1 degrees. So going back over here, this is going to be 3 cosine of 53.1 degrees. And then same thing for the second ball here. It's going to have an x component and a y component. The x component is going to equal, well, we don't know what it's going to equal. We're going to call that v2 for the second ball. That's its overall resultant vector. And so the x component is going to be v2 times cosine of theta, and the y component v2 times sine of theta. And now we can plug those in. So in this case, the x component finally, again, is that v2 cosine theta. And there's our equation for the conservation of momentum in the x direction. And notice what's nice is the only variable in there is v2. Oh, nope, sorry, I lied to you. So it has v2 and theta in it. My bad. We're not gonna be able to solve for anything just yet. All right, let's do the same thing for the momentum in the y direction. And once again, instead of m1 v1, I'm just gonna write m. So m v1 y initial plus m v2 y initial equals m v1 y final plus m v2 y final. Okay, once again, that second ball initially was not moving at all, and so it has no momentum in any direction. So, but also, the first ball was moving completely in the x direction as I drew it, which means it has no momentum in the y direction either. And so in this case, the total momentum in the y direction here was 0, and so it's going to have to add up to 0 for the final total y momentum as well, if you will. And once again, m is also going to fall out of this equation since they all have m in it. And so we're just left with v1 y final, which was that 3 sine 53.1 degrees, and the component of the second one, which was the v2 sine theta. Now, one quick thing to note, both x components pointed to the right, and they were both positive, and I just kind of overlooked it. So, and made them both positive, just kind of looked past it, but it was true, they're totally positive, and we should take that into account. But for the y components, one's in the positive y direction, and one's in the negative y direction, and we've got to account for that, and we can do that here. If I'm just using the reference angle to the x-axis, this would come out to be, v2 sine theta would come out to be a positive number. I've got to factor in that, no, it's supposed to be a negative number for the y component being in the negative y direction. All right. So far we've got two equations, and technically we actually have two equations and two unknowns. We probably have enough to solve this, but let's set up the kinetic energy here as well. So conservation of kinetic energy. So we're now going to have 1/2, and again, instead of m1 v1 and m2 v2, it's just m. So m v1 squared. Notice no components here. Again, kinetic energy and all energy in general is a scalar, not a vector. So 1/2 mv2 squared. Oh, and let's get some initials on there though. And then 1/2 mv1 final squared plus 1/2 mv2 final squared. Okay, once again, every term's got an m, and that's going to fall out of the equation. Every term has a 1/2, and I can technically have that divide out of the equation as well. And we're just left in this case with v1 initial squared plus v2 initial squared equals v1 final squared plus v2 final squared. But yet again, second ball had no initial velocity, so that term goes away as well. So we're left with v1 initial squared, which was 5 meters per second. So 5 squared in this case. And that's going to equal v1 final squared, which was 3 meters per second squared. Once again, I'm leaving off the unit so we don't get lost on the algebra. And then plus v2 final squared. And so what's nice is this last equation, we can actually solve for something pretty easily. We can get v2 pretty quick. Not going to be quite so easy in the other two equations to solve for anything. So if you didn't write this last equation, it turns out we could still do this problem. So it turns out more info than is actually needed has been supplied to make this a little easier, because these can be a royal pain in the butt, where you might need just a little bit of help even doing some of the algebra. When one of your variables is under a sine or a cosine and it's an angle, life gets ugly. So, but we're not going to need that in this case. So one, we can get v2 here, but even if we couldn't get it here, we've got two equations with two unknowns, and we could actually figure it out from these two. It'd be a little bit tricky to do so, but we could. But we're not going to have to. We can get v2 right here, and then we can take that v2 and plug it back into either one of these equations to solve for theta. And that's the approach we're going to take here. So take a look here. 5 squared is 25, 3 squared is 9, 25 minus 9 is 16. Square root of 16 is going to get us v2 final of 4 meters per second. Okay, so we now know that this guy's traveling 4.0 meters per second. Now we need that angle. And again, it turns out Either one of these equations has two variables, v2 and the angle theta, and you can get that theta from either one of them. So I'm just going to use the first one here. And so in this case, we rearrange this a little bit. We're going to get 5 minus 3 cosine 53.1 degrees is going to equal v2, which I'm going to plug in actually 4 meters per second, times the cosine of theta. And now we can kind of solve for theta here. So let's actually write it out a little bit different. So theta is going to equal the inverse cosine of 3 cosine of 53.1 degrees all over 4. That's ultimately what we've got to do here. So we're going to divide through, oh, I lost the 5 minus, didn't I? Let's try this again. 5 minus 3 cosine 53.1 degrees all over 4. Inverse cosine of that. So let's plug that into our calculator. So 5 minus 3 cosine 53.1. Then I'm going to take that answer and divide by 4. And then I'm going to take the inverse cosine of that answer and get, if we round to 3 sig figs, 36.9 degrees. So, and that's this angle right here. And so we can see that the second ball is traveling with a velocity of 4 meters per second at an angle of 36.9 degrees. So a couple things to take into account here and just kind of verify what we said at the beginning. So if we look at the y component of the cue ball, 3 sine 53.1, so 3 times the sine of 53.1, that's going to be 2.4. Let's just round it to 2.4. X component is 2.4 meters per second. And if we now do the same thing and find the y component of the other, so 4 times the sine of 36.9, so 4 times the sine of 36.9, we're going to get also 2.4. We have to remember that this is also negative in the negative y direction. And so now we can see that the velocity of either is exactly the same magnitude but in opposite directions. And by the time you multiply by the same mass, they have the same magnitude momentums, but one's in the positive y, one's in the negative y, and that way the overall y momentum is 0, just like it should be, because again, the initial overall y momentum of the system was 0 as well. So just want to show that we could verify such things like that. You could also take and find out that the overall x momentum still has to add up to 5 meters per second times m, the total momentum in the x direction here as well. And we could do that again by finding these two velocities and then adding up the corresponding momentums times m, and you find out it still adds up to a total of 5m there as well. So a little bit of a pain in the butt here, but totally doable. Now, one thing to note, again, I actually included more info on this problem than is actually absolutely necessary to solve. So, but if I give you one less variable, the algebra again gets ridiculous, and there's a good chance that's not going to be required of you. So I did make this a little easier than necessary, but probably about the same level of difficulty as kind of some of the hardest problems you're likely to see in this section. Now, if you found this lesson helpful, so consider giving it a like. Happy studying.